Okay, so this you can see, this is the first example which we are going to see. Okay, and this is just a plot data method, a function which will plot the data, and this has been made to see the plot of SVM. So anyway, these functions will be there. I mean, we do not need to worry about these methods. What we are going to see is this. So I have already a data file, ex6 data1.mat, if you can see here. It's a MATLAB file where you have the data. So in Python you can also load a MATLAB file. Here I have loaded it. I will plot this data also. So as you know, any data, it will have the data points and their labels also, like which class is it. So that I am going to plot, and then from this sklearn.svm, I have imported a SVC, support vector classifier. Okay, so that's how they have given the name in sklearn. Now with this SVC kernel, I have taken linear, and then we will fit the data points x, and also y we will have to give. Y is the labels, and then we will see how this plot looks like. Again, this parameter I have changed, the C parameter. If you remember the theoretical SVM session, we have seen that there is a trade-off between how much penalty you can incur, like whether you want a large margin and you want, I mean, you can bear some misclassification, or you want a very low misclassification, or zero misclassification, and margin could be less. So that we are going to see with this data point. Okay, so first let us see, maybe first we will just see how the data looks like. So I am again importing this sys function, sys library, and I will exit. I will run only till 52 line. Okay, let us run this code. So we will see, we will be seeing how the data looks like. Okay.
Okay.
Uh, yeah. So can you see this point, this data?
Yes, yes.
This is the data basically which has been loaded, which was there in mat file. So, and you will, so you may ask that how is this yellow circles coming and how are these triangles coming? So I will just cut it and we will do it again. See, here I am calling a plot data function
Mhm.
with x and y. This plot
Okay.
data function is basically nothing but this plot data function. So here I have two markers, this and this, circle and a
Yes.
triangle kind of thing, angle bracket basically. So
Yes.
that angle bracket is with red and the circles are filled with yellow. And actually in our X, if you see, these are the, I have taken the positive ones and negative ones. There are two classes. So wherever the Y label is 1, I mean class 1, I have taken it as positive, and class 0 I have taken it as negative, and I have scattered it. A scatter plot, this matplotlib function you might know from matplotlib, pyplot as plt. So this plt.scatter will scatter the data.
Scatter
This we
data.
have
Yes.
seen in the earlier session of Python,
Yes.
the third session I suppose, second or third session.
Yes. Yes.
So
Third. Third.
yeah,
Mm.
third. So, so this plot data is doing nothing but plotting. So once again, we will see. Yeah, this is the function. This is the data basically. Okay.
Okay.
Now, can you tell me where should I put the line? I mean, this is a 2D data, right? So we can put a line like this in order to separate them, like this, isn't it?
Yes. Yes.
Now, this line will have one misclassification. Can we do something which can we put a line like this? Here, the margin is very less. If you see, the margin will be very less,
Mm-hmm.
but there will be
Yes.
zero misclassification. If you want margin high, then maybe you have to go through something like this. Then your margin will be little high, right? But there will be a misclassification. So that we will see in this code how you can train your SVM in this. So now I am going to remove this exit, and we are going to plot it. I am going to first train a SVM. Okay. With linear kernel means, when I say linear kernel means no kernel. Basically whatever the data is as it is I am taking. I am not
Mm-hmm.
transforming my data. Like in the theoretical session we have seen how you can transform a 1D data into 2D data by doing a parabolic through going through a parabolic function. And we have also seen a 2D data how we can project it in 3D so that both the classes can be divided. But for those transformation you need some kernel, non-linear kernel, right?
Okay.
But here
Yes.
I am putting kernel equal to linear, means there is actually no kernel. There is no kernel. So let us see how it behaves. See,
What is the SVC stand for?
SVC is our SVM classifier.
Okay. Okay.
SVM classifier.
Function.
So yeah, the function, the whole implementation of SVM, how it gets trained, that actually the sklearn people they have defined a class for that called SVC. So we call it support
Okay.
vector machine SVM, but they have typed it SVC, support vector classifier. Okay, so this is my data. Now let us see how it goes. See, can you see this?
Yes.
This is a line which it has learned. But you see, and you know these points which are like crossed. You can see
Mm-hmm.
these boundary points which are what you can say crossed by a line. Similarly, these triangles, the boundary triangles, these are support vectors. And here you can see there is a misclassification here because this data is of this class but it lies here, right?
Yeah.
Now this C parameter, if you remember the theoretical session, is a kind of regularization. It is a regularization. Why regularization? I am saying it's a penalty parameter basically. Okay. So if you penalize your SVM, penalizing your SVM means penalizing your margin. If you penalize your margin, if you increase your basically this, you see, now you can see the margin has become less, right? The support vectors, there are only two support vectors which are at the boundary, these, and this is the support vector for this class, this and this. Still, it is a misclassification, isn't it? But
Mm.
now
Yeah.
the misclassification is not by a huge distance. It's very near. So it is like as you are increasing the penalizing parameter, or you can say the regularization parameter, you are basically penalizing your margin in order to avoid misclassification. You may say that even after penalizing, still you are not able to classify this red one. Okay. So what you can do, you can even increase this parameter more, say 30. Do it for 30. Now we will see. This one was the earlier one where the penalizing parameter is 1 by default. So no
One.
penalty.
Okay.
Now I am going to cut this, so then the parameter will change, we will change it to 30 and then we will again fit the classifier clf.fit and then we will again plot the SVC. See. Now as I have increased from 20 to 30, you can see that this boundary is actually able to classify 100% training data correctly. It is
Hmm.
correctly able to classify 100% training data, isn't it?
Yeah, correctly.
Yes, but what do you say about margin? Is there any margin? See, the margin is very low margin. See, just little bit. Here also you see just this much. This much margin is left. So if you are not worried about margin, but you are only worried that on training data it should be perfect. So then you can increase your penalty parameter, this one, as high as possible, so that it will try to somehow it will try to manage this in order to do zero misclassification and penalizing the margin. But this is not considered actually good. You know why? Because suppose if there is a data point here. Now this data point will be with this boundary, it will be set of like it is of this triangle class. Or if something is here, you will say that this is of triangle class, but actually it is very near to this class and it should be considered as a circle class. So while testing you will get more error. You may get more error because the margin is very low. So what people suggest is you better you go we go with less margin. Sorry, less penalty. So better we go with something like this, maybe 10. Penalize it less.
Yes.
So that now if even if the data points are here or here, at least you can say that it is of this class. Okay. So like that there are things which you can try, and it's all about trying. Like this there on this data set it is only one. So even if you are getting one parameter, one data point on the wrong side, it's okay. On training data you may not get 100% accuracy, but on testing data you will get certainly improved accuracy. Got this point?
Yes.
And this is with 10 penalty. So even with 10 penalty, it has come closer to the line. So this is also fine. Now the data points which are coming here, they will be considered as circle. So
But
that is,
penalty one is ideal penalty.
yeah, penalty one means you are basically not penalizing anything.
Yeah.
I mean, it's a multiplication kind of factor. So even if you multiply anything with one, I mean, it will remain the same, and it is like very minimal penalty. Penalty one is like default. C equal to one is default. It
Mm.
means no penalty. So
Okay.
as you increase the regularization parameter, or you can say penalty parameter, you will be doing good on training data. But I cannot guarantee,
Yes.
and that does not guarantee you about the testing data. Testing data may give you poor results because you are penalizing your margin. SVM is supposed to be a maximum margin classifier, isn't it?
Okay. Yes.
So, so this the purpose of showing you this program. this implementation was just to introduce this penalty parameter, or you can say just to show you, just to demonstrate you how this penalty parameter can affect your data. So in any problem which you are doing, just think about this penalty parameter. On training data, if you have a two-dimensional data, you can always see and see and look how you can put a maximum margin or little less margin and no misclassification. You can it's a trade-off, so you can lie in between somewhere. Okay. Now,
Yes.
and moreover, just notice that in this particular example, our kernel was linear. Your data was linearly separable data. That's the technical term used in machine learning. Linearly separable. Just by a straight line, a straight thing, you are able to separate the data. So this is linearly separable. It may happen that your data is non-linearly separable. Then you may have to transform your data, isn't it? So moving ahead to the
Mhm.
next example, SVM example 2. Okay, this is another mat file. That was ex6 data 1. This is ex6 data 2. Okay, same thing we are going to do here. We are going to plot the data first. Then you see, initially I am going to take a SVM of RBF kernel, radial basis function kernel. It is a kernel which will help you to make non-linear boundaries. It will transform the data in a higher dimension such that on that higher dimension you will be able to put the boundary linearly. Okay, and penalty parameter I have kept it 100. Okay, here in this particular case. So okay, anyway, just don't think about this SVC as of now. This is on ex6 data 2. Okay, so right now just don't think much about this. We will see the data first. So I have used two
Okay.
data set here, ex6 data 2. On this I will show you, and then one more data is there, ex6 data 3. On that also we will see how this SVC works with different penalty parameter and gamma parameter. Gamma parameter will also come into picture with RBF. I will tell you. RBF is nothing but it is also called as Gaussian parameter. Gaussian kernel. Gaussian kernel, you know, na? Kernel like this. Okay.
Okay.
So whatever your data point is, it will try to transform on this function, something like this. Okay,
Mhm.
so anyway we will see that. So I okay, you see this is your data. Which data it is? ex6 data 2,
Exit.
this one. Now this is linear or non-linearly separable?
Yes.
Is this linearly separable or non-linearly separable?
Non non
Non-linear separable,
non-linear.
right? Because
Yes.
no matter what you do, you cannot uh, classify it through a straight thing.
Yes.
Okay. So what we are going to do, we are going to use a Gaussian kind of parameter. Gaussian parameter will do what? It will transform your data such that on the higher dimension it will be able to put a linear thing, and on this data, on 2D data, you will find something like this Gaussian thing. something like a Gaussian thing which you will be able to see like this, isn't it? This should be
Mm.
the case, right? If you are applying
Okay.
a Gaussian kernel, you can learn the curves also, like the non-linear boundaries. Okay, something like this. So let us see. So till now I am just plotting the data. This one I have done. Now when I will cut it, when I will close it, it will initialize this class kernel. I mean this SVM class, SVM object it will create with C equal to penalty equal to 100. Penalty equal to 100 means what? You are penalizing hugely.
But
You are penalizing
yeah.
your classifier hugely so that the misclassification is not there. Okay. And kernel
Okay.
you are keeping it RBF, that the Gaussian kernel, and you are going
But
to fit it.
what is the effect of penalty on our model, SVM model?
Yeah, yeah. So I told you penalty. If you have more penalty, if you are penalizing it more, the misclassification will be less.
Hmm.
We saw it in the assume example, right? If you have
Yes.
less penalty one, there was a misclassification, isn't it?
Mm.
If you have a high
Yes.
penalty like 30, see, I will run it once again. If you have one penalty, very minimal penalty, I mean the default penalty, so there is a misclassification, your margin is high. When you have a high penalty like C equal to 30, then is there any misclassification here?
No.
No, right?
No.
So this
Yeah.
is the case. Similarly, what I am telling here also you have this classifier. Now, if you will not penalize it, it may give a very general boundary which will have lots of misclassification on the training data itself. We can see that. So I will close this figure in order to train this through RBF, and then it will plot the SVM for you. See, can you see the boundary?
Mm.
It
Yeah.
has learned a Gaussian kind of thing, curvy boundary, and can you see the black things?
Yes.
These are support vectors. The boundary, I mean the red and this yellow, the all are like on boundaries they are cut. I mean they are
Mm.
like by a black line they are cut divided. They are being cut. So those are support vectors. Now if you will not put any misclassification, sorry, this what do you say? I will come to this. Yeah, I will again go this with this. Now I am putting C equal to 1 means no penalty. So see,
Mm.
now is this a good boundary?
No.
No, because you see, like this boundary, this is misclassification. Now here there is lot of red misclassified because I will show you. Actually, what it has done, it has taken whole this thing. This is the boundary it has made. And if you see, this is misclassification. This whole bunch of these is misclassification. This is misclassification. This is misclassification. This is misclassification. So many misclassification, isn't it? This is misclassification. This is misclassification. I mean, one class appearing in the other class boundary, right?
Yeah.
That is why I have penalized it a lot.
Okay. Okay.
So I
Got it.
penalize it with the 100. Now with this if you see, What is the misclassification here? See, this is little bit of misclassification here. You see the
Mm.
boundary is like this.
Yes, yes.
Right?
Yes.
Now can you tell me where are the misclassification here? Actually there is no misclassification now. Little bit of misclassification is here, little bit of here. Where
Mm.
else? No misclassification. Little bit you can say
No.
here,
Yes,
little bit
yes.
you can say here. That's it.
Mm.
Right? So you
Mm.
understood what do I mean by when I say that the penalty, you have to increase the penalty. On training data, at least you will be able to classify it in a better way. Okay?
Okay. Okay. Yeah.
Okay. So this is one thing. This I just wanted to show you how a non-linearly separable data also you can classify with SVM using a kernel trick, using a non-linear function on which you can transform your data. Now you will say, where is the data transformed? Data is same. So data is transformed. That is that calculation is going in the library. You will not see it in the plot, because in the plot we are trying to show the on 2D data itself we are trying to show the boundary. But actually it is calculating in a higher dimension and transforming the data in the higher dimension and then classifying it through something. Okay.
Yeah.
Now let us
Mm.
go to the next data. This is the next data. Okay. This is EX6 data 3. Okay. Now on this plot what I am going to do, I have taken the uh, this C param, basically that is your what do you say, penalty. I have taken as 3, and then there is a gamma
Okay.
parameter also, that I have taken 1 and 3. And in loop, basically this is called grid search. It is called what? Grid search. It's a technique. I mean, you may say no, that what parameter should I take? Whether I should take, what is the best penalty? Like whether I should take penalty 1, 2, 3, 10, 100, what? So what people do is, you take a array of penalties and one by one just see on training data how it performs. Okay.
Okay.
So what I have taken C3. I mean, I have actually done it on more number of values, but I found the best one and I have kept them like 3 1 and 3 3. So you see with penalty 3, see this one here I am initializing and here I am training. So I am basically I am doing what, C param I will be 0, so basically 3. C param 3 value will be there. So 3 with 3 penalty, see what it is happening. This is the best what you can achieve. There is still some misclassification, maybe around 10-12 data points are misclassified. 5 of the circles which are misclassified, 5 or 6, and then same number of 6
Plus.
uh, that
Plus.
plus are also misclassified. But this is the best thing which you can get with uh,
Yes.
you can say your penalty 3. If you will go with, again, this is again a thing with
Mm.
penalty, same penalty 3, but this time the gamma I have increased. Gamma was earlier 1, now the gamma is 3. So it's in loop, right? The J is gamma. Gamma, I will tell you, gamma tells you basically the width of the Gaussian. So let us say this will have more gamma or this will have more gamma. So this is like less gamma and this is like more gamma.
Mm.
Okay.
Okay.
So the width is told by this gamma. So now in this you can say you have only 1, 2, 3, 4, 5 plus on the wrong side and 1, 2, 3, 4, 5, 6 circles on the other side. So anything is fine. I mean I just wanted to show you that like this you can choose options. You can check out 10 values here and 10 values here and you can keep on checking which one is better. Okay?
Okay. Okay.
So like this you can actually, and that's what you see all these three data sets, three examples which I have shown. These like such, the way these data sets were there, the same kind of data set you may get while working on some project or something. You may get, I am saying. And like this you
Mm.
can train a SVM which will be a perfect boundary it will make. And I mean what I mean to say is that SVM is one of the best classifier, a two class classifier known, best known classifiers. You know, I mean nowadays neural network has become famous, but before that SVM was just superb. I mean it is a very popular and still it's very popular classifier which can in either it is linearly separable or non-linear. Like I mean either it is a linearly separable data or non-linearly separable data or I mean any kind. SVM will definitely find some way to put boundaries. That's the good thing about it.
Yeah, it's separate data anyhow. It's
Yeah,
classified data
yeah.
anyhow.
You see, the second data
Okay.
set was so much of non-linearity was there. Still, it was with C parameter 100, it was able to put boundaries, isn't it?
Yes. Yes.
So, uh, by this, these two examples are over. Now I will come to a small problem of digit recognition, hand digit recognition actually. Okay, so
Okay.
what I will do, uh, I will show you the problem first. I will run this program first. I will show you what it does. Okay.
Okay.
It's still running. Actually, it's a huge database. I mean, around 50,000 or some images are there. I will show you. So it may take a while to run. Load SVM. Is that file present or not? Just wait. I will look for whether the. Okay, yeah, it's there. So you see, can you see this image handwritten? It is which
Yes.
digit?
Yes. 7.
7, right? So you see
Yes.
now what I have done is, see, actually you see the main function. Like this you can write in Python. So these all are methods which I have made. This one, this one, this one, this one. Like this you have to make methods. Okay, and I am calling the SVM baseline. So SVM baseline is doing what? From MNIST data, it is loading the whole training and testing data. And I have already trained the model. I have already trained the model, this one. This model you can see. It's a 421 MB model, SVM digit recognition model already trained. So that model I am loading, and now I am testing it image by image. So the first image has come like this. Now what is this? 7. You see what it will predict. Actual digit what? 7. Predicted 7. Fine. Now which one is this? 2. Right? It is in loop. It will keep on coming. Okay.
Yeah.
So this is 2. You see. Actual 2, predicted 2. Now you see. Actual 2, predicted 2. Now you see 1. See, actual 1, predicted 1. 0. Actual 1, predicted 4. So it's predicting very well, right? This one is what? 9. Let's see what it does. Predicted 9. This one is
6.
5 or 6.
5.
See, actually it was 5, but it predicted wrongly as 6. Why?
6.
Because that was like, even a human mind can get confused whether it is 5 or 6, right? So by SVM, because it was like 6, so it predicted 6. So this is one time it went wrong. This is 9.
Okay.
This is 0, 6, 9, 0, 1, 5, 9. See how it is predicting now? I will stop this program.
7.
Got it? So basically what it
Okay.
is doing, it is basically what
Can
it
you
is, yeah.
sorry? Can you explain me this program again?
Yeah, why not? I will explain you. Like right now, we just ran. I just ran so that you can uh, get the overall picture what it is
Okay.
doing. I mean, how it is doing.
Okay.
I will explain you line by
Okay.
line.
Okay. Okay.
See, initially what we are doing, we are loading the training and testing data. Okay. Can you see the training data?
Yeah.
See, I am going to print the shape, which will tell how many data is there, right? Okay, it's tuple. Tuple has no attribute shape. Okay. Len will work, I suppose. Actually, this we have to look. See, how many data points are there?
50,000.
See, can you see how many data points are there?
50,000.
50,000 training images are there. Okay, 5,000 image of each digit, 1 2
Mm-hmm.
3 4 0 to 9, and on 10,000 I am doing the testing. Okay, if
Okay.
you directly print the training and testing data, you see. Okay, this is like they have done dot 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 because they cannot show you everything, right? So, but as we saw the 0 and 1, uh, okay. So that we saw that the training data is 50,000 and testing data is 10,000, right? If you want to see the image size, we will see the first tuple. Just for training data I am printing 50,000. 0 was also 50,000, right?
Yeah.
Okay. See, you can see that 784.
Mm-hmm.
Actually, see what is there. This image you are seeing, na, like
Yeah.
written like this. This is 28 into 28 image. So 28 into 28,
Okay.
784. Okay,
Pixel.
and
Okay.
50,000 images are there for training. Such images, and 10,000. Sorry, 10,000 is for testing.
Testing.
Okay, like this it is there. Now, once you have got the training data, now you will say how you are getting this training and testing data through this MNIST load data. So actually you have seen, you see here I have imported the MNIST loader, right?
Mm-hmm.
MNIST loader is not a library, it is just a Python file which I have created here. In this Python file MNIST loader, this load data function is there. So this is the database mnist.pkl.gz. This one, can you see this? 16 MB.
Okay. Yeah.
This is the compressed file. What I am doing here, I am first unzipping it through gzip. I have imported gzip. I am unzipping it, and then I am through cpickle. I am because it was pkl. Now first you will, when you will unzip it, this compression will go off. Then to read this PKL file, cpickle.load f you will do, and it will give you the training validation and test data. And you return that training validation and test data as the data here. So we are interested in
Okay.
training and testing. So for validation, I have just put underscore, means I don't need this. Now training and valid test data I have taken. Now what I will do, similar to what we have seen in the other SVM example, I will train SVM with the training data, 50,000 training data. Now you will see why, you will say why you have done SVM train, where is that SVC and all. So actually SVM train is a method which I have made here. See, it will take the training data, it will initialize the SVC. See, from sklearn I have imported SVM, so svm.svc it will do. It will initialize the object. Then I have trained it. training data 0 and training data 1. Training data 1 is basically the labels. You understood labels? Actually, what was that? So training data 0, it's a tuple basically. Tuple means two things. So tuple, the 0 contains the image, 784 values per row, and the training data 1 contains just one value. Actually the digit it was 7, 3, 4, like that. So these two things, the data and the labels I have used for fitting the SVM, and I am saving that model SVM mlist model.pkl. I have saved it through cpickle. Cpickle I have told you, na? Cpickle is a library through which you can basically persistently write an object or array or anything onto your hard disk. In maybe in whatever you do, C or Objective C or like this, in Java also it was there. There is something called as object persistence, like whole object if you can dump in hard disk. So cpickle does that in Python. So whole SVM object I have dumped after training, after this fit is done. Now this takes time, this takes a lot of time. That is why I have already done it and I have saved it. And through this load function, I am just the same SVM, the saved model, I am just opening it and loading it through cpickle. So here once I have trained it, I will just put comment on this and then I just need to load SVM. So the already trained SVM will get loaded. Okay?
Okay.
It will get loaded because if I will show you how it is training and all, then the training itself take around 15 minutes. Because it's huge, na? 50,000 data points are there. It's not like 200 data point or 300 data point. That two images, like 784 values each image. So it will take little time. So I am not showing you the training part because it will take 15 minutes time. So, but once it's a one-time job, na? So once the model is trained, you dump it and you can load it whenever you require. So through this load function, I am loading the pre-trained SVM. Okay. And then these two functions, test image by image or get test accuracy. These are the two functions which I have used. Get test accuracy will do what, you know? It will test it on all the 10,000 data. I will in fact run this. It will test it on all 10,000 data and give you the result. See, can you see this get test accuracy function?
Yes, yes.
See,
Yes.
CLF with the model. See, I am passing the SVM model and the test 10,000 data, right?
Yes.
So with this CLF.predict test data 0, or test data 0 is basically all the images, 10,000 images. So for each data point I am basically predicting it. So this is the prediction. And then I am seeing how many are correct. Okay. So the test data 1 is the actual correct value and this is the predicted value, prediction. And this is the actual digit what it was. So if both are equal, it will come 1 and I am summing them. So 1 plus 1 plus 1, how many number of time it came equal? It will calculate number of correct thing. This also actually takes time because 10,000 images it has to predict.
Okay.
And then it will find out the number of correct thing and then baseline classifier using an SVM and this of this value is correct, it will print once it runs and executes the whole program. So this is one way of getting the test accuracy, but you are not visually seeing what is happening. So to show people how visually it is doing, I have made another function test image by image. Here also I am passing the same model, train and the test data, but in this function, what is happening? What is happening? I am in loop, in for loop, in the test data, in for loop, I am taking each image. So image is there in 0, right? So that image
Yes.
I am taking and I am reshaping it in 28 by 28 so that it becomes an image. Okay. And then I am plotting that image, and this is just for prediction, like clf.predict, the whole thing you can predict. So this is the predicted value and this is the actual value. Actual value is in test data 1. I told you, test data is a tuple. 0 is 784 values, which is the image, and the test data 1 is a label. So this is the label, actual and predicted. So I am printing actual and predicted. Got it?
Okay, got it.
This is test image by image. So in this, when you plot a mixed data image, each image will pop up and then it will print what it has calculated, like that, image by image. And if you want to do it on all 2000 all together, you can call this function get test accuracy, which is running currently. And this is plot a mixed digit just to plot the figure. So it will just create the PLT figure and all, and whatever image you have passed, 28 by 28, this one, it will plot it. So the plotting goes like that. Now it will take some, I think, around 5 minutes or 6 minutes it take.
This why you're using 28 by 28?
I mean, the data is like that only.
All data is like that.
Yeah. The enriched
10,000
data,
data.
have you heard of? Enriched data is a very famous database of handwritten digits.
Okay,
It is 28 by
okay,
28 only.
okay.
I know
If
28 by
any point,
28 is very small.
yes, if any point is missing or any shape is missing, it could be possible.
Yeah. I mean, usually by your phone or mobile or whatever image you take, it is very high resolution. No? It is 180 by 1080 by 1080, or 720 or
Yes.
something. This is just
Yes.
28 by 28. You see, it has run the this one, get test accuracy. Out of
Okay,
10,000, 94, I mean 9,435 figure, it got correctly predicted.
okay,
And now that image by image, now this function has run test image by image, and now this image by image has come.
okay,
It will go until 10,000 like this. So I will not go
mm,
like that. So I will
okay,
stop. So this is the whole program, okay?
okay.
This you will say, why are you doing this handwritten digit recognition and all? This
Mm,
program was first uh, built in 1982, and this was the you can say one of the first artificial intelligence program, first artificial AI software, you can say, in 1982, which was used by US um postal services. In America,
okay.
they have got zip codes, like in India,
Yes.
we have pin codes, right? So I will tell you the application. In India, you see on Indian postcards, there is a box like this, right?
Mm,
In earlier days, like you have got some on your postcard, there used to be a box like this, right? Here you were used to write
yes.
your address and all, or maybe here, or maybe on top right or something like this, where you write pin code, right?
Okay.
You remember this thing?
Yeah, yeah,
In
I know.
postcards, usually it used to be. So similarly, in US there is something zip codes are there which you have to write it on in these boxes in their postcards. Okay, so they made this software, and as these boxes are fixed, right, it's fixed, so anybody has to write the digits in this only, handwritten digits, and people used to write it by their hand like pen or whatever. With pen they used to write, so that was handwritten digits, right? But these boxes are
Okay.
at fixed position. So what this software used to do, first they will just extract these boxes, and then they try to predict what is there in box, and with that they can, I mean, there is no manual labor required, automatically it can club all the postal cards or all the postal courier or whatever it is there. It can club the all the things which are of same zip codes. So to automatically read the zip codes, uh, this MNIST database was used, and in the for the first time this software was made in 1982 around something, and it was used by US Postal Services. It is still used by them. Nowadays they have used some neural network for this, but it was huge, and it gives, I mean, it was one of the most successful software in those days. So that is why this MNIST database is very famous. And with these classifiers, people try to do the classification testing and all, and they used to get the accuracy.
So if suppose I overwrite on any one of digit,
Mhm.
so is it identify like I overwrite for first I write 4, then I write 5 on number
Okay.
4. So is it under identify correctly? Is the 5 of
I
4?
mean, you wrote like two and then you did three.
No, little complex. Say I written 4, then on that I make as 5.
You are making it five. Yeah. So
Yes, yes.
that is the point. I mean, you saw how that five was detected as six because
Hmm.
somebody has written five like this.
Yes, yes, yes.
So sometimes, so it depends how you are overwriting. If you are overwriting it properly, then definitely with the pattern it will get. But if you are vaguely doing writing things, maybe it get confused by five or six or something. So it's anyway it's not 100% accurate. Still you can see that you saw the result. It was like out of 10,000 it detected 9,435
Hmm.
correctly.
Yeah,
And
yes.
I know few CNN architectures, I mean deep neural network architectures, which gives almost 99% accuracy on MNIST. So maybe just 100 or say some 80, 70, 80 images it won't be able to classify. Other than that, everything is classified with deep neural network. I mean with this convolution neural network. So people have reached till 99 points something also. And actually, if you will see
Okay.
the MNIST database, there are few, I mean, on in some blog or some article I have seen, there are a lot of images which you will never be able to tell what exactly it was. I mean, there are a lot of images where people write so vaguely that even the human mind cannot identify what it is, what it was. So then how do you expect a machine to do that? I mean, sometimes, machine can also go even above human mind. So,
Hmm.
so it's like that. But yeah, mostly whatever the sensible writings and whatever you write, it will detect. You saw when we were doing that image by image, you saw na, how it was predicting correctly.
Yes, yes, yes.
So this was the one usage of SVM which I showed you on this digit and written digit data. Okay.
Okay, yeah.
Any further questions you have, you can ask.